Today I'm going to talk to you about robotics, and in particular, robot design. And if we look at the robotics community at the moment, there is a huge amount of work looking at how we can exploit large language models and other large AI models. Be this for robot perception and vision, robot control, planning, robot-human interaction. But one area which I think we're really not exploring and not exploiting enough is how we can use these large AI models and LLMs for robot design. But first of all, I need to motivate why is robot design important? Shouldn't we just focus on doing more reinforcement learning, developing better controllers, better robot perception? But I believe if we want to close the gap between human or animal performance and robots, we can't do this purely through machine intelligence. We need what we call embodied intelligence. We need physically intelligent bodies that allow us to offload or augment some of the computation in our brain such that we can interact intelligently with the world around us. So what does this actually mean? So when we say embodied intelligence, we mean rather than just having a brain and a controller that acts in the world, this brain and the controller and the actions we select go through our body, our dynamical processes, and our morphology, and then interact with the task in the environment. And we're interested in how we can design these bodies to exploit low-level sensory motor control, compliance, variable stiffness, or even distributed sensing and actuation. And this is how some of the fantastic biological systems around us get their capabilities to interact intelligently with the world. Be it with a soft octopus, where we have a decentralized controller with different limbs, a spider's web, where we exploit the morphology and structure to provide mechanical and sensing capabilities, or even this mountain goat, which uses its reflexes and variable stiffness in its hooves, to be able to traverse incredibly steep cliff surfaces. So in my lab, we really look at how we can design robots that exploit this embodied intelligence. So for example, we do this with soft robots, looking at how we can develop compliant systems that interact with humans, how we can develop more anthropomorphic, dexterous manipulators, so developing hands that can have variable stiffness and compliance, such that they can perform very delicate but also very high force motions. We're looking at morphing robots, so how we can use changing shape and morphology to be able to locomote through the Alps or very varied terrain, and also sensorizing structures, so we can get robust and intelligent interactions with the environment. But this is tricky. We have a problem. We have a bottleneck. This currently relies on human intuition, biological inspiration, and to some amount, generative approaches to design. And the challenge with approaching the robot design from an embodied intelligence perspective is we need multidiscipline expertise. We care about the material science, we care about biological inspiration, but we also need to understand the mechanical engineering, the computer science, and the control theory that ties this all together. It's also an intractable design space. How do I parameterize the design for my octopus, where do I still capture the intricacies and the low-level details which are so important? And also, how do I define a goal or a fitness function? If we want to optimize for something, how do I define something that really qualitatively describes, for example, the capabilities of my goat here to be able to traverse this cliff? So we started thinking about how can we use human and AI interactions to be able to assist with this multidiscipline design problem. And we looked at, could we use a human and robot to design, through LLMs, a robot together in a collaborative manner? So we worked with GPT-3 to look at, could we ideate, could we design, could we select the details, and finally, could we generate and fabricate a robot based on interactions with humans and an LLM? So we started with questions, the engineer talking with the robot, with the AI, how can robotics support agriculture, looking at design selection, and using the LLM to help identify or predict what would be apparently good materials and parts. And the nice thing about this is the human could have a conversation and use that conversation to guide the discussion. But in addition to this, we could use the ability to generate language to actually create designs that can be rapidly generated into fabrication or systems. So we can generate the STL, or files that describe the morphology, the structure, and also the code that can be used to accompany this. We can also even generate the instructions for how to assemble this robot in a meaningful way. So with this, we could then, through conversation, just using a native form GPT, we could design our robot gripper for harvesting tomatoes. And this was relatively successful. We have a gripper, we have a code. It makes sense if you were going to build it without using LLMs, probably you'd arrive at something similar. But this accelerated the process. We could cut out a lot of the dead time in terms of looking for motor specifications, in terms of material selection, in terms of some of the additional work that would gone around this. So we've been looking at how can we use LLMs to empower interdisciplinary design, such as this for embodied robotic systems, and looking at how we can have human engineers interacting with AI for high-level discussion, using this to accelerate the design process, but then offloading the technical implementation to the human. And this works really well for a number of reasons. One, we can tie into this interdisciplinary expertise. We can find out, we can ideate over areas where we may not be comfortable with. But we can also, as I say, shortcut and identify some of the very tedious problems very rapidly. But we also have problems here. When we ask questions in the area of expertise of the engineer, we have an ability to sanity check. But once it goes outside this region, we then get to the point where, how do we trust? How can we actually have some metric or some uncertainty in this answer such that we're making meaningful decisions? So based on this initial kind of exploration of how we can use LLMs in this way, we wanted to look more kind of generally. How can we use large AI to assist in robot design? What are the challenges and opportunities here? I mean, one very big thing is we can empower lots of people to make this domain far more accessible, because there's a big learning hurdle to hardware. And this stops a lot of disciplines from being able to leverage this hardware. But within the robotics domain, there are a number of really exciting opportunities for how we can leverage these large AI models. So I'm going to talk now very briefly about this encoding, contextual prediction, qualitative feedback, and also how we can design and achieve more contextual and grounded behaviors for iron-bodied robotic systems. So the first one, how can we use large AI models to assist in robot design? And the first thing is encoding, or describing our design space. So we heard earlier about language, how we have our encoding, our decoder. It's very central to language. And design can have the same. We can have a language for design, and we need an encoder and a decoder in exactly the same way. Now, if we look at perhaps the best example of encoding there is, we can look at DNA. This encodes all the information for our genetic makeup. And it's been shown that DNA, the bases and their structure, can be very well represented in a grammar. It has a vocabulary, it has rules, it has structure. And this is very powerful in terms of encoding. And we can do the same thing with robot structures and morphologies. So we can create a grammar or a representation, which has a vocabulary, it has a structure and rules, and ensures that we design robots that are realizable. They're not nonsensical. So what we can do then is create our robot grammar. So there's an example here of some prior work we did in this area, and look at how we can represent our robot design, our encoded robot design space in a text-based manner. This gives us a very scalable encoding. It can be bio-inspired, because we can build and use our LLMs to propose different grammar types. It also offers human interpretability, which is very important at this stage, and allows us to generate many very complex designs. But the important thing is the decoding. If we can represent our design, we also need to be able to decode it into something that can be fabricatable. And here, LLMs, again, can be very powerful. Now we can go for our encoded grammar robot design and decode them into something that can actually represent the design in machine-interpretable code. So for example, in the morphology, the structure, the kind of physical geometry, we can translate these to STL files, which can then describe the 3D structure. We can then also go one step further and slice these and then generate these to files which can directly generate and then fabricate on a 3D printer. Likewise, in terms of the control and the decision-making, we can create behavioral trees that can describe the different processes. So now we have the ability in language to encode and decode our design space for a robot. But that's great. We can describe lots of robots, but how do we know what's a good robot? How can we efficiently find, for our application, what should our robot look like? And this is where prediction comes in very important. We want to be able to evaluate lots of designs and assign and a merit to how good they are. And typically, we might do this with a physics model or a simulation. So we have our robot, we have our controller, we run it in simulation, and there's been some superb, fantastic work here looking at how we can use simulation to optimize robot design. But typically, this would be very single modality. We might be able to simulate, for example, the deformation, the stress, the strain, or perhaps some dynamic locomotion. And this doesn't account for many of the kind of environments we see. And we end up with these significant sim-to-real gaps. So we can't rely on these simulations to be able to capture much of our complex robots' interactions with the environment. So, for example, we could have our soft robot finger, and we can predict its deformation. But that is not going to tell me much about how well is this soft robot finger going to perform in, for example, a robot cooking task in my kitchen at home. So what we're interested here is, can we use LLMs or large AI models to be able to inform or refine or describe better the environment in our physics model? So for example, can we look at what are likely objects I might have in my kitchen? What color are they? What texture they are? To make a more rich and contextualized physics model. And likewise, can we offload some of the challenges from our physics model to our large language model? If I push an egg off the floor, it's going to most likely crack. Now, that's something that's really hard to capture in a physics model. But can we use, even with natural language, the kind of prediction and modeling capabilities of the LLM to be able to at least inform our physics engine that that's the likely case? So we can have this relationship between the model of the kind of the prediction capabilities of the LLM and our physics model. And in this way, we can predict more complex behaviors beyond perhaps the statics, dynamics that we might typically use from our physics models. But we've still got a problem. How do I now describe what is a good robot? At the moment, we would typically use a fitness function. So I might have my robot hand that I'm trying to optimize for, and I might, for example, have a single fitness function that describes how well this performs. It could be how quickly you can do a task. It could be the payload it could reach. It could be the dexterity or some very quantitative metrics which describe its performance. But these do not translate to how well my robot is going to work in a complex environment. How well is it going to work in my kitchen to perform a complex tasks? How do we describe the performance of this robot? So we're looking at, can we move away from a single kind of metric, a very quantitative metric, to something very qualitative? And this is something we're very good at humans. How can we qualitatively describe the performance and use that to update the design? So for example, we have our robot hand cooking in the kitchen, and it's doing some kind of task, be it the washing up. Now we can have a qualitative-based description. For example, it's too slow, it leaves liquids, it's too noisy. And use this then, based on qualitative language, to be able to update the design. So this allows us to move away from very single fitness functions to more general qualitative metrics that describe the behavior of our robot. So just to be slightly more illustrative about this, we're looking at this in a couple of domains at the moment. So one is robot cooking and food design. So we're looking at how we can make food products which are both nutritious, but also have lower impact on the environment. So we're looking at basically making plant-based drinks. But currently, we encode our design space, we use a robot to make lots of these beverages, and we use very manual viscosity or human feedback, what they say, in terms of 3 metrics, how well this performs. And this gives us very limited feedback with which we can optimize our plant-based metric. We're now looking at taking direct human feedback, spoken qualitative description, and looking at how we can use this to update our recipe to improve this robotic making process. And this gives a far more expressive way of describing the process, and yet we can use the LLM prediction capabilities to be able to make suggestions as how we can update our recipe. So we can do this for plant-based milk. We're also trying to make personalized scrambled eggs, but we're a little bit further away from the ethics approval on that one. And we can also do this for robotic robot fabrication. So can we use robots to make robots, and then again use qualitative fabrication on these to drive this feedback loop? So here we're making little aerial vehicles that this robot forms from paper. It sticks them together, it throws them, and we get some video representation of how well these fly. So we can now use qualitative feedback rather than purely quantitative metrics to be able to describe this from video to text to inform this design space to create fitness functions that can capture more varied behaviors. So talked about robot design. We have our robot, we've designed it, we're happy with it. We want it to be able to interact with the environment. So the exciting thing about embodied design in robots is this interaction with the task or the environment. And this could include a human, it could be a human environment, or just your standard agricultural field. But we want to look at how we can use LLMs to help the robot or the design of the body to better utilize some of the prediction or understanding or context we might have of the task and the environment. So for one example, this is our robot which is looking at trying to help feed someone fondue. Very, very, very slowly. So it forks the bread, hopefully then the fondue as well, and then slowly the cheese makes it up to the person's mouth. So we're looking at how we can use our soft robots for assistive, very slow feeding, and also assistive dressing and other kind of systems. But, oh, there we go, it made it. Fantastic. But we need to be able to understand, to be able to fluently interact with the humans, we need to be able to understand from their expression, from their feedback, when are they full, when are they ready? So how can we use, again, large AA models to do this? And also, can we make decisions on the behavior? Yeah, it goes a bit off course from here. For example, can we predict when the bread is, when the cheese is when the cheese is hot, when it's likely to burn the person? Can we make predictions about this which allows us to inform safe decision-making about the behavior? So we can create these more fluent human-robot interactions by having a little bit more contextual prediction. And there's one test that we want to be able to do. The end goal for much of this embodied robotics is taking the Turing test, which again has been discussed today, so this idea of having human answering questions to an AI and a human and being able to distinguish which is which. Can we have an embodied robot Turing test? So this is now where we ask a human and a robot to complete the same task. But from the outcome, can we identify which is human or robot? And this is very interesting because, first of all, we require the capabilities to be able to do this. But secondly, we also require some understanding of how a human might do this. And that requires some understanding of the context, the goal, and also the context or the restrictions you might have placed upon you. So we're really interested in using this as a benchmark to look at what are the capabilities of our embodied robot systems, and can LLMs give a perceived potential for robots of understanding human environments and tasks. So, just to sum up, LLMs and large AI models are extremely powerful tools for roboticists. But we need to think a little bit more outside the box, perhaps, than just looking at control, learning, perception. There are many other ways that we can leverage their huge predictive powers to look at how we can inform the future of robot design and also the future of robot capabilities. They really provide this mean of grounding decisions, which is something we're really lacking in terms of physics, modeling, and simulation, and also human-robot interactions. But obviously, we have big questions and challenges, as many people have already mentioned today, in terms of validating or assigning certainty to these predictions. And also, how do we ensure that we still encourage creativity and also ensure that the technology development continues in this way? So, I'm really excited, looking forward to look at how we can exploit large AI models for robotics, and also how should we design large AI models for roboticists? What do they need? What data should they use? How do we interact with them? And how do we make most use of them going forwards? So thank you very much for listening. Just to thank my team that have done all this fantastic work, and I'll open to questions. Thank you.
Thank you, Josie, for that inspiring talk. Do we have any questions from the audience? OK, I will get us. Oh, all right, one more here.
Well, thanks for the talk. So this is a just pretty dumb and general question. So as you show in the video, which was really exciting, these robots do tend to move really, really slowly. Is it intentional because of the safety issues, or is it because of the limitations of the actuators, or is it because of the limitations of the control? Is there any reason why they have to be this slow?
Very good question. One, safety reasons is often the case. This can go a lot faster. The actuation limits is more of a limit than the controller limits. So the control in real time or quasi-real time is not a challenge, but actually getting actuation that has the torque, especially if we want to do torque feedback, is a little bit more of a challenge. So it's a mixture of safety reasons and also actuator limitations.
Question right there.
Thanks, Josie. Is the Turing test the best thing? For your examples, I could imagine being better than the human would actually be the goal rather than being exactly like the human.
That's an interesting thing. So I think there's two things. There's one, completing the task and how well can you complete that? And there's another, can you complete that in a way that it's indistinguishable from being a human? And I think they're slightly different things. And I think in some cases, we don't care how you complete the task as long as it's done well. But there's other things where it's important that it is completed in a way that a human does. So for example, if you're going to kind of perhaps a doctor or something like that, there's a lot of comfort as a human for it being performed in a way you'd expect. So I think I completely agree with you. There's many cases we don't care how it's accomplished, just that it is. But there are some interesting cases, and also it's an interesting test, not just of the robot's physical capabilities, but its ability to kind of have some perception or some appearance of understanding human norms and experiences where that can be useful.
Oh, question right here. If we can get a microphone. Oh, all right, be loud.
I was wondering, for the loop with GPT-3, with, I want to do this, give me the STL code, how frictionless is it in practice?
Good question. So the question was about how much friction there is in generating STLs or G-code when using GPT. So good question. So I think the bigger challenge is the STL to G-code part. There is a limit on the complexity of the model that you can then export to XTL. So STL, relatively frictionless. STL to G-code a little bit more challenging because then you've got a myriad of settings in how you do your slicing. But for the kind of designs and structures we were looking at, that was a fairly seamless process, but I think going more complex than that, there's going to be similar limitations. So there's a bit more need there to have kind of an additional sanity check or something in the loop there.
Maybe time for one last question. Oh, there you go.
So do you see potential for this paradigm of using language models to, say, design a robot as being useful in educating, younger generations, 10-year-olds designing their own robots with the assistance of a language model? Like, is it there yet?
Yes, very, very good question. So we're just starting to do some experiments also on the kind of education, learning science of specifically within design, how can we use this as an educational tool to assist in this area? So I think very much so, because we've got this debugging problem, and it's not just in software, but it's also in hardware. And I think that's what really makes design, and specifically robot design, very challenging and has this kind of bottleneck to entry, as you can get to this point there where the debugging at a hardware level is very, very hard if you don't have some kind of expert-guided tuition. So I think that's another very powerful role that LLMs can play within robotics.